Okay, so this is going to be a part A and part B thing today, and I apologize for that, but let's just keep moving through it. And I apologize for the focus issue on this webcam. I don't know what to do about it. If there's anyone has any suggestions, please let me know. All right, so getting back to when you I'll try to stand over here because I think it's when I wave my arm in front of the screen that's when it screws up. All right, so when you take what's called a barrel, now a barrel is 42 gallons. And so when you take a barrel of what's called petroleum out of the ground, and we'll talk about oil wells in a little bit, it is a combination of those alkanes ranging from n equals 6 to n equals 20. And the what you do then, and the chemical engineers in the class will appreciate this, you then perform fractional distillation, which we're not going to teach you how to do fractional distillation here, but basically it's a way of separating mixtures of liquids with different boiling points into the finished product. So motor gasoline there, gasoline, I mean, it's kind of like, 6, 7, 8, 9, 10, those range, it kind of has some distribution that's peaked around 8. And diesel, is sort of, I think it's 14, 12, 13, 14, 15, 16, and so these various products, now diesel, that's the same thing as distillate, and I don't know the etymology of that word, but basically those top 3 there are gasoline as you know it. So when you distill a barrel of crude oil, you get around 19-20 gallons of gasoline. You get around 10 or 11 gallons of diesel, essentially, and around 4 gallons of jet fuel. And it works out just perfectly, actually, in this country. That's precisely the kind of the ratio of consumption of petroleum in our cars and our trucks and our planes. Okay, and then you go from there, and there's various other products there, including solid products at the end, including things like asphalt and stuff like that, a very high end. But we're primarily interested in the first 3 there. So then you go back up here, and you use the chemistry you just learned to perform these calculations of the energy content of these various products. And it works out 1 gallon of gasoline, we calculated 122,000 BTU. It's a little bit higher than that when you add in a few corrections. Around 124,000 BTU is what we usually use for that. So, for example, gasoline. All right, let's do a little fun little conversion here. If I have, if I have my car, all right, and I have a gas pump, and I have the hose going into it there. Gasoline. All right, and let's say, okay, think about when you go to the gas station. Basically, you can sit there and you could time it, but you see the gallon meter turning, and so roughly it takes, I mean, to fill a 10-gallon tank, say, it might take a few minutes. So let's use 3 gallons per minute. So it would take a little over 3 minutes to fill the 10-gallon tank, which sounds about right. Okay, so if we take 3 gallons per minute times 60 seconds per minute times 124,000 BTU per gallon times 1,055 joules per BTU. Sorry about that, got shrunk in a little bit. So basically this is a way to calculate 3 gallons per minute. Oh, this should be 1 over 60, sorry. Okay, so that's 3 over 60 gallons per second. Minute per second. You can see I'm trying to get joules per second here. And if you work this out, okay, let's see if I can do it in real time here. 3 divided by 60 is 1 over 20. And so if I divide that by 20, roughly, 60, 1 over 20, that's somewhere around, say 6,000 times 1,000. So it's around 6 million joules per second, or 6 megawatts. So when you go up to Wawa, half awake, fly up to the gas pump, jump out, get the gas pump working with your credit card, and plunk the nozzle down into the gas tank, and turn it on and go. You are delivering the equivalent of 6 megawatts of power into your gas tank. And so it's like, I mean, imagine if you were trying to convey 6 megawatts of electricity. Okay, you maybe don't have a feeling for that yet, but it's simply remarkable that so easily and so cheaply we have the access to this much equivalent power, and then we fly out of Wawa in a few minutes and we're on our way. So liquid fuel, these liquid alkanes, are a tremendously useful source of energy. So we really want to understand why we want to replace it then. Okay, because if it is such a useful form of energy, okay, well, there better be a very good reason for replacing it. Now, of course, we're not going to talk about global warming and things like that, and we are going to talk about depletion of these chemicals. But anyway, I wanted you to appreciate just what a great, why we use it so much. All right, now I'm going to jump ahead here. And I'm not sure what time I'm up to, but because this ended up being in 2 parts, and now I've lost focus again. Okay, I don't think that's that bad. I'm going to jump ahead to what an oil well looks like. All right, so, and yeah, we've lost our focus. Maybe if I turn on all the lights. Okay, it seemed to like that. Right. Now the problem is I gotta turn these off again. That's probably gonna lose it. Nope, it's still there. Okay, good. All right, let's keep moving. So this is a typical oil reservoir. It's called a conventional oil well, and there's various geological aspects that have to take place in order for you to have a oil reservoir. And the first one is that you have a layer of say porous rock like sandstone with biology of some sort. All right, so over eons, millions of years, there's a layer of rock there, and so this could be at the bottom of some shallow sea a million years ago, millions of years ago, and so plant matter, fell down here, and it formed this sort of porous rock that also has organic material in it, and then layers of rock came down on top of it, and that pressure and heat over years converted that biological component in that porous rock into alkanes. And so over the years you might have sort of, I'll put in parentheses, hard rock, a hard rock layer on top of that. So that's kind of the first geological aspect. There's steps of this. Millions of years you have this sea bottom, and then somehow over more millions of years a layer of harder rock got deposited on top of that, and then you have more material above that. Okay, so those are two steps, and then there's a third step, which is somehow there's been a geological event that has caused this all to, bow upwards like that, so that you have this sort of upward cap, upside down cap. And what happens is that the alkanes in here are going to be under huge pressure, thousands upon thousands of pounds per square inch. And that's going to want to force them to go up. So basically, the pressure of the rock is causing the alkanes to go nearer the surface. But they can't because of this hard rock layer here, which forms like this cap. And so you get this reservoir as shown there. That's one way to do the geology. The other way is shown here, where you basically, instead of having this sort of curvature type geology formation, what's happened is, for whatever reason, like a mountain formed over here, the layers got tilted. And then what happens is that you can have a fault, like an earthquake, and it causes things to shift like that. And so then basically this sort of top seal in the porous rock forms like a reservoir. And now, it's not like it's filled with gasoline there. I mean, basically this is all still rock. It's just that it's kind of porous, and so the liquid can kind of flow through the rock. And then what you do is you put down an oil well. So here's my oil well. So you drill a hole. First you find out where that reservoir was, and you hopefully drill a hole all the way down to it. So the idea is that this surrounding rock, surrounding this hole you put in the ground, is that reservoir, that porous rock filled with gasoline and stuff like that. You'll notice that there's the word gas here. That's because it's all alkanes, and so you're usually a natural gas well in the same place. The gas just is higher up, and so the further down you go, it becomes liquid. And so you put down this hole. Now you have to be very careful as you put down this this oil well, that you put down a casing at the same time, because otherwise all the oil in here is just going to go blasting up this hole and out into the surface. And so as you're drilling, you're also lowering a casing. And the bottom of that casing has perforations, so the oil can flow in there and go up through a tube in the middle. And ideally, what has happened is that as you're putting this tube down in the ground, this pipe, you are simultaneously keeping it capped off, or trying to. And you've all seen the movies where, okay, they keep drilling and drilling and drilling with this tube, and if it's not, you know, capped off the whole time as it's going down, you get the gusher, you know, and then they work to close the valve. So, you know, that's basically what's called a conventional oil well. And a conventional oil well, well, this is showing where you get oil and stuff like that. If you go back up here, right now, you know, if you go way back up to the for, you know, this chart here at the beginning of the course, you know, annual oil production is somewhere around today is a little between 80 and 85 million barrels a day. So around 80 to 85 million barrels every day comes out of the ground. And of that 80 to 85, here, about 70 million of it is what's called conventional, which is basically those vertical wells that I just showed. And that is really, if you think about it, cheap way to get oil, because you don't have to do anything. You just have to plunk your oil well down, and you start getting oil. Now, before we talk about unconventional oil, there is a little bit more to it. Okay, and I know this is a little bit, you know, make this a little bit smaller. So, let me go back up to the board here and make my oil well. So let's make our oil well. Okay, so we have our oil bearing and a room. Oil bearing strata. And up here's the ground, and we've plunked our oil well down. Okay, and you know we have some sort of valve up here, so we're getting our oil. Now, so when you plunk down your oil well, then I mean it's just a matter of, you know, adjusting the valve here so it's not like totally blasting out. You can capture it in pipeline or some tanker or something. And so, you know, I mean, you don't have to do anything to make this work. All right, so what happens though is that works for a few years, and then your oil well stops, it stops flowing out. And it stops flowing out because it runs out of pressure. It doesn't stop because it runs out of oil. There's still a lot of oil down there. It's just there's no pressure to push it up to the surface. And so what you do is you put down a well of, for example, water. And that water then pressurizes the strata, the reservoir, and so now, okay, it sort of pushes and you start getting oil flowing again. And for example, all of the fields in Saudi Arabia currently take, there's basically, the sea over here, and that's where they get their water from. And so they're basically pumping seawater down into their oil reservoirs in order to allow it to continue pumping in. And there's, in certain circles where they're trying to figure out, for example, how much oil Saudi Arabia has left, there's a lot of discussion about what's called the water cut, which is basically how long they can continue to do this. Meaning what's going to happen is that as time goes on, you see a little bit of that, most of this is oil, but some of that water comes out of the well too and has to be separated. And the fraction of water will go up with time. So in principle, Saudi Arabia, for all of their oil wells, they can track what's called the water cut, or the water percentage in their oil, and they can probably project out exactly when that well is going to run dry, how many tens of years in the future. Of course, they keep that a highly guarded secret because they don't want anyone to know when they're going to run out of oil. But anyway, these are what's called secondary techniques. And there's different ways of pressurizing the oil reservoir. One is like just dropping seawater down in there, and the other is, for example, you can pump compressed air down there. That's sort of a kind of a cleaner way to do it. It takes a lot of energy, but the various ways to do that. And so currently, most of our conventional oil wells on Earth, well, I don't know if it's most, a lot of them are under secondary conditions where they're being artificially pressurized. All right, now, that's conventional. And let's talk about unconventional, particularly fracking. So we've said that, if you have porous rock with oil, all right, there's oil there. Now the thing is that what happens if we don't have that geological formation of a curve or some fault to form a reservoir? It's still there, and we still like to get it. So what you do is you do horizontal drilling, and so basically there are a lot of formations in the world where there's a shale strata with oil. And horizontal drilling is where you drill, like it sounds, sideways. So you have a drilling mechanism where you can drill straight down, and then basically the bit is like this clever mechanical device that can then start turning sideways and make your borehole sideways in the horizontal strata. Now, what happens is that shale, there's a lot of shale, especially in the United States, that's oil bearing. What will happen is you form this borehole. Okay, you think about it, the way this works is that you can't have casings and perforations, anything like that. You basically just kind of have to have a borehole and then some sort of tubing mechanisms to bring it up to the surface. And so if it were porous, it would just sort of flood in there. Shale is a harder rock, but not so hard. And the oil can flow into the hole you've made horizontally, but it will only flow for a little bit, so you have to do what's called fracking. And that's where you've pumped down water under high pressure. And that causes the shale around here to crack. And so, especially near the borehole. So you basically, you pump down a hydraulic, very high pressure water, and that cracks the rock. And when it cracks the rock, it allows the oil to flow into the borehole, and you get production. And this goes under various names. It's called sometimes just horizontal drilling oil, sometimes it's called fracking oil, sometimes it's called shale oil, but whatever it's called, that's what's going on. And the thing is that if you go to this chart in U.S. oil production, so this is U.S. oil production. Oh, damn it. Okay, we're going to try the same trick.